Now, a normal distribution, it's a very important statistical data distribution pattern occurring in many natural phenomena, such as height, blood pressure, lengths of objects, scores on tests, etc. There's many things just by their very nature that follow a normal type of distribution. Certain data, when graphed as a histogram, data on the horizontal axis, amount of data on the vertical axis, creates a bell-shaped curve known as a normal curve or a normal distribution. Normal distributions are symmetrical by nature with a single central peak at the mean, and that represents the average of the data. The shape of the curve is described as bell-shaped, with the graph falling off evenly on either side of the mean. And we're going to see that that graph falls off and it creates these tail regions, and that there is symmetry about the center. Now, 50% of the distribution lies to the left of the mean, and 50% lies to the right in a normal distribution. The spread of a normal distribution is controlled by the standard deviation. The smaller the standard deviation, the more concentrated the data. The larger the standard deviation, the more spread out. Now, the mean, median, and mode are the same in a normal distribution. Since it's a unimodal distribution, the mode is found, the most frequent observation, which is the center of the normal distribution, and the median represents where the 50th percentile is, and since the distribution is symmetrical, the mean and the median are equivalent here. Now, normal curves are bell-shaped, unimodal, and symmetrical. So here's an example to the right of a normal bell-shaped distribution. Notice at the center, the location of the center, or the peak, that location is denoted by mu, the mean. Now we have transition points on a normal curve, and that's where curvature changes. These transition points define the locations of mu minus sigma and mu plus sigma. So these are the values of the distribution where we are one standard deviation below the mean and one standard deviation above the mean. Now, the location of the transition points is helpful in determining the location of points in question on a normal curve. We can tell which points are within one standard deviation of the mean and which ones are not. And that's going to become very useful when we start looking at probability distributions and drawing a picture to find out what range of values we're looking at across this bell-shaped curve. Now, a normal distribution does have a particular function. We're not going to address that here, but if you do take a calculus-based statistics course, you will learn that, the functional value for a normal curve. And recall, those of you that have taken calculus, our transition points or inflection points occur when that second derivative is set equal to 0. That's where our curvature changes. So we're curving upward to downward to the mean and downward to upward to the right tail. And so the location of those transition points, once again, do have a very important meaning on a normal distribution. We can locate one standard deviation above the mean and one standard deviation below the mean. Now recall that as the standard deviation increases, the curve flattens and spreads out. Notice that the bell shape remains the same. And notice that we didn't change our center either. The center remains the same as well. So if the standard deviation is increasing, our curve is flattening and spreading out. And that makes sense because standard deviation is measure of spread on average away from the center. So higher standard deviations are going to result in bell-shaped curves that are kind of small and fat. Now, as the standard deviation decreases, the curve gets taller and thinner. Once again, the bell shape remains the same. Therefore, the standard deviation, the average spread away from the center, if it decreases, our data is becoming more compact. Most of our data is kind of falling now towards the center of our distribution, so our graph tends to get taller and thinner. Two important concepts to understand when talking about bell-shaped curves. Bell-shaped curves all have a bell-shaped resemblance, but some are tall and thin and some are short and fat, and that all depends on the nature of the standard deviation and how spread out our data is. Now, in this example at the right here, notice the shapes of the two normal curves.